Okay, so our next and our last speaker for the session today, but don't leave yet after that, we have some questions we have for you, is Zhongtian Mao from Charlie Campbell's group at the University of Washington. And they've got some cool work on their new insights on their degree of rate control analysis. Zhongtian, it's all yours.
Thank you. I'd like to share some recent work we did on the degree of rate control analysis. So the rate determinant step or rate limiting step is a central concept in the chemical kinetics. But the definition of the rate limiting step is usually not clear. People may say it is the bottleneck of the reaction mechanism with the smallest forward rate constant, or people may say it is the step with the highest energy of transition state. The original purpose of degree of rate control, DRC, is to strictly define which step is rate limiting. The definition is a partial derivative of logarithm of the rate with respect to the logarithm of the forward rate constant of step I. Keep the equilibrium constant and all other rate constants constant. An easier equivalent description can be the partial derivative with respect to the negative Gibbs free energy of the transition state in step I over RT. Keep all other Gibbs free energy constant. It is if you change the energy of a transition state in the reaction mechanism, how much the overall rate will change with this energy change. With the DRC analysis, you can easily define which step is rate limiting because in the rate limited step, the DRC equals 1. If we use the definition based on the Gibbs free energy, we can easily extend the application of the DRC from the transition state to any other species in the reaction, like the intermediates, the products, or the reactants. So this generalized DRC tells you if you change the Gibbs free energies of one species in a reaction, how much the overall rate will answer to this energy change. In some of my following slides, I will use this small reduced g instead of the negative capital G over RT. So using degree of rate control analysis, you can simplify a very complicated reaction mechanism into a few species with non-zero DRCs. And these species, we call them the rate controlling species. You may think the DRC is just a mathematical concept, but in fact, they are closely related to the experimentally accessible data. Or you can say you can measure the DRC in experiments. This is an example. It's a carboxyl reaction mechanism in water-gas shift reaction with 8 elementary steps. As I mentioned, the DRC of the rate limiting step is 1. In the real world, the activation energy of step 5 here is 0.47 eV. In this case, step 6 is the rate limiting step. So you can see the DRC of step 6 is 1. But if I manually increase the activation energy of step 5 in the calculation, you can see the DRC of step 5 increase and the DRC of step 6 decrease. Until you have a high enough activation energy for step 5, it takes over as the rate determinant step. Then step 6 goes down to 0. In experiment, you can use many methods to determine the rate limited step, and you see the transition state in the rate limited step has a DRC of 1. The other part is about the DRC for the catalyst-bound intermediates. Their DRCs are proportional to their fractional coverage, theta, and the proportional factor, sigma, equals a summation over all steps. The xk here is the DRC of step k. Nk is the number of sites that participate in the step. For example, if we are here, step 6 is the rate limiting step. Then we see 2 sites in step 6, so this factor equals 2. For CO adsorbate, its DRC equals -2 times its fractional coverage, about -1.9. If we are here, it's step 5, take the rate limiting step. Then this number equals 1. So for CO adsorbate, it equals -1 times its fractional coverage, about -1 for its DRC. This is a simple example for DRC analysis, the Langmuir-Hinshelwood mechanism. If we assume step 3 is virtually irreversible and A star is the most abundant surface species, this is the rate equation. You can easily calculate the DRCs for species in the reaction mechanism. Transition state 3 has a DRC of 1. It means step 3 is the rate determining step. For adsorbate A, it has a DRC of -2, which equals -2 times its fractional coverage, about 1. For all other species, they have DRCs close to 0. And after we know the basic properties and basic rules of DRC analysis, here is the first application for computational catalyst screening. This is the energy diagram of the methane steam reforming on rhodium and ruthenium catalyst. If you change the catalyst from rhodium to ruthenium, you can see the energy of species change and the rate will change. This is exactly what DRC want to tell you, how much the rate will change if you change the energy of species. So we start from the definition, it's a partial derivative. So we can reorganize the definition as and rewrite as a total differential like this. And then we can integral from the reference catalyst, which is rhodium here, to the energy of the new catalyst of interest, which is ruthenium here. And this is the equation. You can use the equation to calculate the relative rate with respect to the reference catalyst using the degree of rate control of species. However, it's usually not easy to conduct integral in the research. So we further assume the DRCs are independent of the catalyst material in a range of interest. And this is the final version of the equation. You can see if we know the degree of rate control of species with the reference catalyst, and we know the energy change from one catalyst to the other one, we can calculate the relative rate from one catalyst to the other one. Remember, only a few species has non-zero DRCs, so only these species contribute to the summation here. Once we have the DRCs on the reference catalyst and we know the energy of species on the catalyst, we can calculate the energies of only the rate controlling species on a new catalyst and use this equation to calculate or estimate the relative rates on the new catalyst. Here is the result. In the DRC method, we search the catalyst in a space formed with the energies of the rate controlling species. For example, here, they are the adsorbate CO and the transition state CO. Each catalyst of interest have a position in this DRC map. If we only consider the first two rate controlling species with the largest DRC, these two species, we can estimate the relative rate relative to the reference catalyst using this equation. We can see the relative rate estimated using the DRC method is very close to the number estimated from the actual DFT calculation. Remember, when we derive the equation, we assume the DRC is independent of catalyst material. However, this assumption is not always true. If you look at this DRC map in the Noskov-Bligard descriptor space, you can see in large regions, the dominant DRC species does not change. It's okay. But if you move the system from one side across the boundary to the other side, the DRCs can change rapidly, and this assumption does not hold. If, like from rhodium to ruthenium, the DRC of carbon can change a lot. If you include the carbon into the estimation, it can cause more error than just use the two simple, most rate controlling species. To summarize, in the DRC method, we establish the reaction mechanism on a reference catalyst, for example, rhodium, and then calculate the DRCs to find the rate controlling species. And remember, you can also determine the DRCs in experiments. Then we go to a new catalyst, calculate the rate, first calculate the rate controlling species energy with accurate method, and then estimate the rate on the new catalyst. So our key strategy is to reduce the reaction mechanism to a few rate controlling species, and this allows us to treat them more accurately. For comparison, the Norskov-Bligard method calculates the energy of species on several typical catalysts first and establish the linear scaling relationship. Then they obtain the new energies of species on a new catalyst using this linear scaling relationship. But this step can sacrifice some accuracy. For example, the binding energy of CO in iridium from linear scaling can be about 0.5 eV higher than the actual DFT calculation. And then they calculate the rate using the not that accurate estimated energies using microkinetic model. So their strategy is they reduce the work for calculating the energies for all species by estimating them with a few descriptors. For us, it's a few rate controlling species. Another application is about kinetic isotope effect, KIE. This is a reaction of CO2 hydrogenation on copper. If you use hydrogen, the energy diagram is the red one. If you replace hydrogen with deuterium, you can see the energy will change and the energy diagram will be the blue one. The rate will also change. The logic is the same as the catalyst screening method. The only difference is now it's the relative rate from hydrogen isotope to deuterium isotope. I summarized the DRCs and coverage of species in the reaction. First, looking at these two columns, from hydrogen to deuterium, DRCs does not change much, so the assumption is solid here. Also, there is only a few species contribute to the KIE. Plugging the number of these three species into the equation gives RH over RD equals 0.4, an inverse KIE. The full microkinetic model gives 0.45, very close to the number from DRC analysis. It's interesting here because people usually think the rate determinant step determines the kinetic isotope effect. But here you can see this is the transition state in the rate determinant step. But hydrogen formate, they are not, but they contribute to the KIE. Acetic acid is in the rate determinant step, but it has no effect on the KIE based on the DRC analysis. After I finished this project, a question came into my mind. It is, in textbook, you can see the KIE is a result of the isotope substitution. It changed the 0 point energy and changed the activation energy, and thus changed the rate. Since we proved that for a multi-step reaction, you can calculate the KIE using degree of rate control. Then my question is, can I express the apparent activation energy for a multi-step reaction using the degree of rate control analysis? And the answer is yes. I will not show the detailed derivation here, but just the final result. E apparent of a multi-step reaction equals RT plus a summation over all species in the reaction mechanism. This summation is actually an averaged enthalpies of species weighted by their DRCs. And since only a few species has non-zero DRCs, only a few terms in this summation are effective. Let's start from something simple, a Langmuir-Hinshelwood mechanism. From the same equation, we can easily calculate E apparent equals RT plus the energy of transition state 3 minus 2 times the energy of adsorbate A. If we use our equation, this one, and plug the DRCs into this equation, we actually get the same result as the actual value. Another method for apparent activation energy is the energy span model from Kozuk and Scheik. They said the apparent activation energy is the highest energy span in the reaction energy diagram, which is transition stage 3 minus A star minus B star in this case, but this is not correct. Usually the energy span model doesn't work for surface reactions. To show how it works for a more complex reaction, we use the hydrogenation reaction we studied before. If we use the reactants as the 0 point for the energy, then only 2 species has DRC, non-zero DRC and non-zero enthalpies. For comparison, I calculated the energies using the rate with a microkinetic model in a range of temperature. The Arrhenius plot gives E apparent equals 209.78 kilojoules per mole. In this table, I have the DRCs and the enthalpies of species. We can plug all these species into this equation. It gives 210. But this is not necessary. You can just plug these 2 species into the equation. It gives almost the same result. And both of these two numbers are very close to the number from the Arrhenius plot. Here are the new equations I mentioned in my slides, the two similar equations for catalyst screening and kinetic isotope effect. This one is the equation that relates the DRC of intermediates with their fractional coverage. And this is the apparent activation energy result. I would like to thank Professor Cambell and group members in Cambell Lab. I thank my advisor, Charlie Campbell, for giving me this chance. And also thank DOE for supporting this project. And thank you for your time.
All right, thank you, Zhongtian. Thank you for a very nice talk and that information about degree of break control. So we've got a couple of questions and we have some time for more if any come in. The first question is there any reason that total DRC is 1?
For a simple reaction, James Domestic proved an idea. But if you want a general proof, it is like for each step in the reaction, there is a KBT over H times some function of the concentration distribution under reaction condition. The total DRC sum up to 1 only for transition state. You can assume if you increase the energy of all species, all transition state in the reaction mechanism, it is equivalent to if you put the reaction in a world with a higher frequency, everything there is faster or slower. If you put the same factor for all transition state on this factor, you plug it into the equation, you can get it add up to 1. But it's always true, it's solid.
All right, and another question asks, why does the energy span model not work for surface reactions?
So this is a very good question. So for energy span model, they start this model for organic chemistry. The basic difference between organic chemistry catalyst and surface catalyst is usually in organic chemistry, they have only one catalyst site. It can be a homogeneous catalyst or enzyme. So their energy span model states it's the apparent activation energy. The apparent activation energy equals the highest transition state minus they call this stationary state. If it's one site catalyst like enzyme, this is the lowest energy with the most stable binding species to the catalyst. There's no difference. It's good. But if it's for surface catalyst, in the energy diagram, you see the stationary or resting state is A star plus B star. But if you look at the surface under reaction condition, you cannot see A star plus B star. You see almost all A star. If you look at the two sides, it's actually A star plus an ignorable fraction of B star. So it's actually consistent with the energy span model, but you have to redefine the resting state in the energy diagram.
Amar, I had a quick question.
Yeah, go ahead.
So I can't type questions into the Q&A, I think. My question was, when you have linear free scaling and the free energies of A star and B star and C star scale with each other, how do you account for that when you use the chain rule? Because each of those are dependent on something that isn't clear to me.
Yeah, this is a good question. So first, the DRC is a mathematical partial derivative. Like, let me go back to the original one. Yeah, it's the so when you change, for example, you change from one catalyst to another one, the energy of all species will change by some amount. But what we do is we just look at the final energy. We don't look, we look at the energy change independently, because if you change the catalyst or do some other change, energy of all these species will change. We just look into the energy change and the result of the energy change on the rate separately, one by one. So it will not affect if they are related to each other. And also you can look at the paper published by Philip Christopher on ACIS catalysis. This is the only DRC paper published by their group. They actually did the thing you said. They relate the DRC analysis with the linear scaling relationship. So the final result of their paper is, in our equation, we have the summation of the DRC times the energy difference. In their method, they replace this DRC as a weighted factor of the DRCs of the species which are related together, and the energy change here is not the energy change of individual species, it's the energy change of the descriptor. So for example, this can be sigma the combination X of carbon star times the energy change of binding energy of carbon plus the combination of DRCs for oxygen binding energy times the energy change of oxygen binding between these two catalysts. Hope this answered your question.
All right, great, thank you.
All right.